I'm giving an update to the S382 Transiting Exoplanets book, which is about a decade old now. Now, this book covers the things that you need to know to study exoplanets. And the two real-world photographs on this title slide are from a conference that I attended about 3 years ago, which was in Vietnam. It was an exoplanet specialist conference. And I was delighted to discover when I left the lecture theatre at one coffee break that a colleague who is from Portugal, I think, and works in Germany, was recommending this particular book to a young PhD student from Asia as being the thing to read if you move on to do research in exoplanets. So I gathered from the module team that people were feeling a little bit like you were missing out because exoplanets are often in the news, and so everybody's very aware of the fact that this field is moving incredibly quickly, and the book is 10 years old. And so this lecture is just to allay some of those worries, really. And I just wanted to give you this analogy. So this is a textbook that was used in pretty much every graduate program in physics in the US when I was a graduate student in the 1980s, and is probably still used by PhD students in physics throughout the world. And the first edition of this book was actually published in 1962, and the main underpinning material was derived between 1861 and 1865. And in order to actually successfully get a degree, the most important thing is you have to understand the fundamentals, and the fundamentals don't change. So a degree should make it possible for you, if you choose, to go on to the next stages in an academic subject area, which obviously if you just read news stories on the internet, you're not going to be able to then jump into the academic subject and become a practitioner. So the degree will allow you to demonstrate degree level mastery of the material and methods of the subject, and should allow you to understand and engage with the things that you see in the news, the developments that are happening in the exoplanets field since the book was published. And a degree should allow you to develop and demonstrate transferable intellectual skills. And I designed the Transiting Exoplanets book to do all of these things. And I was really pleased when the Institute of Physics reviewed our curriculum and highlighted this particular part of S382 as treating important topics in what the Institute of Physics regards as the core of physics. So this book deals with the fundamentals, and if you want to really properly engage with the subject, you need to understand the fundamentals, and these don't change. So the book is probably not as dated as some of you might fear that it is. So the book was co-published by CUP, and as I've said, it's recommended for incoming PhD students around the world because it's a really good sort of overview of the fundamentals. And it's also used by undergraduate students at other universities. And I know from talking to colleagues that it's used at Oxford, at Cambridge, at UCL, and at Harvard, though possibly for honesty's sake, we should say that at Oxford and Cambridge, this is regarded as first-year material rather than third-year material. So what you all want to know is, what have we learned since I wrote the book? And an awful lot has happened. When I wrote the book, there was only about 300 known planets, and those were mostly hot Jupiters. So they were sort of up in the top left-hand corner of the graph on the left-hand side of this slide. And since then, we've added about another 4,000 known exoplanets. And we now know of about 700 planetary systems that contain more than one exoplanet. And we know about a great diversity of star, planet, orbital parameters. So we've really expanded our knowledge. And a lot of this is due to the Kepler satellite and many, many small transiting planets, which are presumably rocky, have been added by the Kepler Space Telescope. So this is to sort of put a timeline of exoplanet space missions, so that you can see the context of where we are now. So right now we're about 2/3 of the way across this timeline. So KUPS has launched, and we're waiting for the James Webb Space Telescope to launch. So on the top part of the graphic are all of the space missions which are dedicated exoplanet missions, from the first one, the Carole Space Telescope, which was a joint French-European Space Agency mission, which found Carole 7b, which was a very important groundbreaking first low-mass exoplanet that transits, all the way out to the planned missions, which haven't launched yet, Plato and Ariel. So the ones on the top are all dedicated exoplanet missions. The telescopes on the bottom are observatory type space telescopes. So they're doing all sorts of other things in astronomy as well as exoplanet work. So the Hubble Space Telescope has done an enormous amount of work on exoplanets, and Spitzer has done some fabulous work looking at exoplanets in the infrared and actually detecting the secondary eclipses where the exoplanet goes behind the star. Gaia is flying at the moment, and this is actually an astrometry mission, and it will discover some exoplanets by being able to measure the movement of the star as a planet orbits around it and pulls on it with its gravitational pull. And very much at the forefront of many astronomers' minds at the moment is the James Webb Space Telescope, which should launch this year. And you'll hear more about this next week. So one thing that I'm particularly excited about is the Ariel Space Telescope, which is the very, very last of these planned missions. And this is going to be the first dedicated spectroscopic mission for exoplanets. All of the others, all the way from Carole to Plato, which is planned to launch in about 6 or 7 years, all of the others are basically photometry. So they're basically designed to find transiting exoplanets, and Ariel will do spectroscopy. And much of the power of astrophysics is built on spectroscopy, which allows us to actually interrogate the light, to learn things about compositions and temperatures and physical conditions. So Ariel, I think, is going to be a very powerful mission, and I'm quite involved in Ariel myself. So hopefully some of you will recognize the graphic on this slide. So this just gives us a schematic of where the various known exoplanets are found. So the radial velocity discoveries require Echelle spectroscopy, where the light from the star is spread out into very, very fine resolution so that we can measure the small Doppler shift due to the pull of the planet on the star. So the radial velocity discoveries are restricted to nearby stars. The transit surveys, like SuperWASP, which is mentioned in Chapter 2 of Transiting Exoplanets, are sensitive to more distant host stars than the radial velocity discoveries, because a transit survey is just collecting all of the light from the star and forming a light curve rather than spreading that light out very finely. So transit surveys are sensitive to more distant stars, and sort of the ultimate in that is the transit survey that's been executed by Kepler, which, as you've seen, is a space telescope, and that points in a particular direction in our galaxy. And the transiting exoplanets that Kepler has found are about 10 times more distant than the typical radial velocity discovery. So that figure is figure 1.21 from the Transiting Exoplanets book, and most of the new 4,000 exoplanets that have been discovered since the book was published were found by Kepler. And these discoveries are generally distant and hence faint. And so they're difficult to do detailed follow-up studies on. So what have we learned in this 10 years? So by looking at the 4,300 exoplanets that we know about, we can start looking at the demographic population of the exoplanets in our galaxy. Now, there's obviously, as the book discusses, quite strong selection effects. So most of these objects have been discovered either by the transit method or the radial velocity method, and both of those very much favor hot and warm planets that are orbiting close to their host star. So it's no surprise that the exoplanets that we know about are almost all closer to their host star than the Earth is to the Sun. So on the graph here, the x-axis is semi-major axis in astronomical units, and 1 astronomical unit is the distance of the Earth from the Sun, of course. And you can see almost all of those points of the known exoplanets are closer into their host star than the Earth is to the Sun. And what you can see in that graph is that there are some missing planets. You would expect, if you didn't really think about it, that there would be planets of all different radii at all different distances. But in fact, the intermediate sized planets are missing at the close radii. And the reason for this is because they're very hot. And when a planet is very, very close to its star, then the star's intense irradiation can cause the planet to lose mass. And so this actually sculpts the population demographics, and you see this sort of bite of planets missing between about 3 Earth radii and 10 Earth radii in this graph. And this is called the Subjovian Desert. So planets which are smaller than Jupiter tend to be missing, and they've basically been evaporated away until you just end up with a rocky core. And so as you get down to very small masses, then you do find planets again, because the radiation from the star is not sufficient to actually evaporate the rocky surface very quickly. So this is an alternative view of that same feature, and this is a figure taken from a theory paper. And so rather than things that have been directly measured, what's plotted here on the y-axis, rather than it being the size of the planet, which you can measure for a transiting planet, it's actually the mass of the planet. And for most of these objects, you need to make a sort of theoretical assumption to get the mass of the planet. But the reason I included this was I think that this is a really beautiful paper with a really beautiful idea that basically shows that if you migrate a planet inwards, if you have a mass that would put you in the Subjovian Desert, then the planet disrupts due to tidal forces. So it's a very, very nice piece of astrophysics. I'm not sure if the hypothesis is actually right, but it's an extremely elegant piece of work, so I just wanted to feature that. So I've told you about the Subjovian Desert, which is the dearth of planets around the size and mass of Neptune in very close orbits where the planet would be hot or warm. And it turns out there's some interesting sculpture of the demographics of the really low mass planets as well. So this is a figure from a paper in 2018, and it shows planet radius versus orbital period. And in grey are points that are from the Kepler survey. So these are all planets that have been detected by Kepler, plotted on the same graph. And you can, if you look at the grey points, you can probably just about see that there's sort of a diagonal line sloping downwards towards the right, where there isn't quite as many points. But this wasn't very clear when the grey points were all that we had, and in fact it wasn't clear until you collapsed all of the orbits together and made a histogram of planet size. It's very clear that there's sort of a valley in this histogram at a size of about 1.5 Earth radii, and there's more planets, more smaller planets and more larger planets, but missing planets at around 1.5 Earth radii. And this was hypothesized as being, again, mass loss, that low mass planets lose their atmosphere if their surface gravity is insufficient to hold on to it against the irradiation from the host star. So again, this is a sculpting of the population demographics. And this became very, very much clearer in the paper that this figure was taken from, which was published in 2018. And this basically recalibrated the data for a subset of the grey points using astroseismology, which is the pulsation of the star, which allows you to know the stellar properties, the stellar mass, and the stellar radius very precisely. And our knowledge of exoplanets is almost invariably limited by the precision with which we know the parameters of the host star. So by using astroseismology to give you a more precise stellar mass and stellar radius, you're then able to get a much better precision on the planet radius. And so in these red points, it now becomes very clear that diagonally sloping sort of gently down to the right, there are missing planets, which shows you the effect of irradiation causing planets below this so-called radius valley to lose their atmosphere because they have insufficient gravity to hold on to their extended atmosphere. And one of the very, very hot off the press results, which I actually learned about this morning when I was preparing this lecture, is that TESS, which is currently flying, it's a NASA transit survey mission, which is basically looking at all of the brightest stars in the sky to basically fix the problem that we have with the Kepler known planets, that they're orbiting stars that are too faint and distant. So TESS is focusing on bright nearby stars, including the faintest, least luminous stars, the M dwarfs, and it's found sufficient M dwarfs now with planets orbiting them that you can actually see the same effect in exoplanets which are orbiting M dwarf stars. You can see that the planets which have insufficient gravity are losing their atmosphere because they're being irradiated by the host star. So we're in a golden era for discoveries of bright, nearby, transiting exoplanets, thanks to NASA's TESS mission, which is flying at the moment. And I'm now going to change gear a little bit and tell you about some radial velocity discoveries. And now we're focusing in on the very, very closest neighbor stars to the sun. So this graphic shows our sun at the bottom in the center, and the edge of our solar system is the Oort cloud, which is a roughly spherical cloud of small, probably icy bodies, which actually extends out to about 2 light years from the sun. And obviously, usually in S382, we use parsecs as our unit. However, this graphic was actually designed for, being intelligible to journalists and members of the public. So this particular graphic is given in light years, and the conversion is about 3. So 2 light years is about 6 parsecs. No, is that right? No. 2 light years is about 0.6 parsecs. Yeah. 1 parsec is about 3 light years. Yeah. So there's a project that's been going on for about 6 or 7 years, which is called Red Dots. And this is looking for planets which are orbiting the sun's very closest neighbor stars many of which are the very dim M-dwarf stars. So these very near neighbor exoplanets was discovered about 4 years ago in 2016, and it's the very closest exoplanet to the Sun. It orbits the very closest star to the Sun, which is an M-dwarf star. It's a terrestrial planet. It's got about 1.3 times the mass of the Earth, and it's in a pretty temperate orbit. It has a year which is equal to 11.2 days, but because the star is so dim, its temperature is not that different to the temperature of the Earth, and it's about 4.2 light years from the Sun. Now, though it's in a temperate orbit, Proxima Centauri b is probably not a very good prospect for life, and that's because the M-dwarf star that it orbits has an enormous amount of stellar activity. So things that are sort of analogous to the Sun's coronal mass ejections happen frequently and energetically. So the planet, which is really very close to the star, is constantly being bombarded by high energy radiation and particles, so it probably can't hold on to an atmosphere, and it's probably not a good prospect for life, because complex molecules would be continually damaged by radiation. So I'm now going to take you on a little sort of tour of the neighborhood. So on this slide, in the pale purple, the line is pointing to the galactic center from the Sun, and in the pale grey is a line which is sort of indicating our equatorial plane. So this is the plane that the Earth and the other planets orbit in, and the line that's almost vertical is pointing to right ascension 0, declination 0. So just so you're oriented on the sky. So if we step out a little bit, then the nearest star is Proxima Centauri, which has a much brighter companion, Alpha Centauri, and more or less in the same direction as the galactic center. The next nearest star is Barnard Star, and that, like the Sun, is a single star. It doesn't have stellar companions. As you step further out, you can see about 23 star systems here, out to a distance of almost 4 parsecs. And they're color-coded to indicate the spectral type of the star. So this is from the Recon survey, which is featured in the early parts of the Transiting Exoplanets book. And what you should see immediately from this is that most of these nearby neighbor stars are smaller, dimmer, and redder than the Sun. They're almost all red dwarf stars. So in, I think it was 2017, the Red Dots collaboration discovered a planet orbiting Barnard Star, which then was called Barnard Star b. And I have to say, I'm happy to say I'm one of the co-authors on this discovery, though I do feel, you know, slightly like the sort of football player who hangs around by the goal waiting for somebody to pass them the ball so they can tap it in, because this paper had about 22 years worth of data which was needed to find the extremely low amplitude signal, which is indicated here by the black sinusoidal wave, amongst the noise in the data, because this is a low mass planet orbiting a star which has some stellar activity, so there's quite a lot of noise to beat down. So I only joined the team shortly before the paper was published, but nonetheless they let me be a co-author, which was very kind of them. So this is another view of that data, and here you can see the data spreading over the many years it was collected, and you can see how that sine wave relates to the data, and an enormous amount of work went into doing the detection of that signal amongst the data where the noise is much higher than the amplitude of the signal. So this is the closest exoplanet orbiting a single star to the sun. And it will actually be the closest exoplanet to the sun in about 30,000 years' time, because the sun and Barnard Star B and the Proxima star system are all orbiting around the center of the galaxy, and they're not orbiting in lockstep. They've each got their own orbit, and so actually Barnard Star B will come closer to the sun, and the Alpha Centauri system will go a little bit further away from the sun. So in 30,000 years' time, Barnard Star B will be the very closest exoplanet to the sun. And this is a super-Earth planet with about 3.3 times the mass of the Earth, and it's in a temperate orbit with a year of 233 Earth days. And its temperature is about 100 degrees Kelvin, so it's very much closer than, very much colder than the Earth, and it's orbiting at about the snow line. But this is quite an interesting planet. So this is an artist's impression. We don't actually know what the planet looks like, but this is an artist's impression that was put together for the press release. And what's interesting about this particular planet is that actually it's got the same temperature as Europa, which is one of the moons in the solar system, and is in fact thought to be one of the best prospects for the possibility of finding life elsewhere in the solar system, because Europa has an icy crust with a subsurface ocean, and it's possible that Barnard Star B might be similar, and those subsurface oceans could indeed form habitats for life potentially. So another Red Dots collaboration was published at the beginning of last year, and these were a system of 3 planets orbiting another red dwarf called GJ 1061, and GJ 1061d, the most distant of these 3 planets, is actually in the classical liquid water habitable zone, orbiting the 20th closest star to the sun. So this is obviously a planet that's quite interesting from an astrobiological point of view, because it's probably got a similar temperature to the Earth. And then finally, the most recent Red Dots collaboration was published last summer, and this is 2 super-Earth planets orbiting another red dwarf. So I think this is the 12th closest star to the sun. It's the brightest M-dwarf star in the sky, and there are 2 super-Earth planets orbiting around it, and one of them has a temperature of about 70 degrees C. This particular star is extremely benign. It has very little stellar activity, so it probably has a nice stable environment for those planets, and if they have atmospheres, they can probably hold on to their atmospheres. Now, the temperature might sound a little bit too toasty for life, but one thing that's interesting is that we think that life on Earth actually originated in the subsurface sort of hydrothermal vents, where the water was probably at a temperature of about 70 degrees C. So this object too is quite interesting from an astrobiological point of view. So in total, the Red Dots project has discovered 7 planets orbiting 4 of the nearest stars to the sun, and I've circled the 3 of them which are astrobiologically interesting. So this is really, I think very, very exciting. And for people like me who grew up with the sort of classic Star Trek series on TV, the fact that there are so many of these small rocky planets that might potentially provide habitats for life is just, it's like our wildest dreams come true, really. And I sometimes can't believe that I actually get paid to be part of this project. So what have we learned since I wrote the Transiting Exoplanets book? Well, I think we've learned that planets are ubiquitous. We've also learned that low mass planets are the most common type of planets, And low-mass planets are generally present around M-dwarf stars. And M-dwarf stars are the most common type of star. So something like, I think, 75% to 80% of the stars in the galaxy are M-dwarf stars. And those low-mass planets orbiting M-dwarf stars include planets which are astrobiologically interesting. So that's interesting for the philosophy of our place in the universe and how special are we. So we've also made some planet discoveries outside of the Red Dots collaboration. So I've done quite a lot of work when I first got into exoplanets in very large collaborations, and I decided that really what I wanted to do was lead my own project, and I had an idea which I was able to actually successfully execute. So we've discovered some planets in a small team led by me, predominantly populated by Open University researchers and PhD students. So I've put the YouTube link up there to a lecture that I gave about a year and 3 months ago, where I talk about this particular project. So this is the Dispersed Matter Planet Project, and these are planet discoveries that really belong to the Open University. And this is an image which we commissioned from the artist Mark Garlick, just to sort of illustrate how we found these planets. So these are close-in, hot, rocky planets that are losing mass. And I was able to work out which stars to look at because I could see the signature of the mass that they were losing just by looking at an archive spectrum of the star. So this was our first planet discovery, and we've discovered 4 or 5 planets orbiting this particular fairly nearby main sequence star, and it was made very, very efficiently because we knew already what sort of planets to look for. This was our second discovery, and this is a giant planet which is orbiting a pulsating star. And if a star pulsates, it makes doing radial velocity work very difficult. So people could have found this a decade earlier, but they sort of gave up because the star misbehaved, and we went in with some conviction that there was an interesting hot planet there and found it. And then the third one that we've published, I was hoping to show you a movie, but sadly Adobe Connect garbled the movie capability. But this is a really interesting system. So we started off looking at star A, and we were looking for low mass planets orbiting star A, and the first thing that we found was star B, which is an object which is either the most massive possible brown dwarf or the least massive possible star. So it's right on the boundary of whether it's massive enough to sustain thermonuclear fusion. And it's in an elliptical orbit, orbiting star A every 506 days. And then we also found, orbiting star A, what we originally set out to find, which is a super Earth with about 2.5 times the mass of the Earth in a 6.7 day orbit around star A. So this is interesting because it is the tightest known binary system to have a planet orbiting just one star, and it forms some challenges for how planets form and evolve, because you wouldn't really expect it to be there. So yeah, so that's our artist's visualization of the little planet orbiting the brighter of the 2 stars with the brown dwarf or very low mass main sequence star in a much more distant orbit. And then I've told you about TESS, which is looking for transits of planets around bright nearby stars. So we looked at the TESS data for the first of our DMPP targets, and we actually have found a transit. And we sort of thought that we were quite likely to find transits because you would expect the material that the planets are losing to be concentrated in the orbital plane, which means that we're probably looking edge on. And so we published this paper last summer, And our discovery is the red dot on the period versus transit depth plot. And so as far as I know, this is actually the shallowest transit that has been discovered in the test data. And that's because we knew already that the star was special. So we put special effort into analyzing the data. So this is something that we're quite excited about. So I wanted to give you a little bit of a general update, having shown off a bit about my discoveries. And I included this slide because this is from about 2 years ago, and this is this new submillimeter telescope array ALMA, which has done some really beautiful work resolving the protoplanetary disks around forming stars. And the reason I really liked this was because it was the first time ever in astronomy, I think, where the actual data looked more beautiful than the artist's impression which accompanied it. So the picture here is the actual data of the protoplanetary disk around the young star HL Tau, and you can see that the disk has got these rings where there's missing emission in it, and it's thought that those rings are probably carved out by planet formation, and particularly at around 10 o'clock there's a sort of ring with a gap in it, and that may very well be the location of a planet which is forming from that protoplanetary disk. I think at the end of the Transiting Exoplanets book, I say the next big thing looks like being direct imaging of exoplanets, and that has been correct to some extent, I think. So there's a very nice instrument called SPHERE, which is on the Very Large Telescope at the European Southern Observatory at Paranal in Chile. And this is a coronagraph, so the instrument is designed to block out the starlight. So what you can see in the image here, in the top left-hand side, is the sort of residual starlight where, you know, the star is obviously very, very, very bright and you can't get rid of all the light completely. So there's a little bit of leftover light from the star that hasn't been completely got rid of. But what you see there then are two giant planets with a mass of about 14 Jupiter masses and about 6 Jupiter masses. So these are two giant planets orbiting a sun-like star at a distance of about 300 light years. So direct imaging is particularly good for planets which are distant from their host star, and it works best for young planets where the planet is still forming, and so it's radiating away its heat of formation. So the planet is radiating in its own right. So this was published last summer, and it's a really nice result. So there are some updates on exoplanets within the OU curriculum. So after you've studied S382 and done your other two taught modules in the physical sciences curriculum, I think many, maybe all students go on to the science project module. And I did write an exoplanets topic into the science project module. So this is an opportunity to take what you've learned in S382 and apply it to a particular area within the field of exoplanets, to apply what you've learned and deepen your understanding. So this is an obvious place where there are updates elsewhere in the OU curriculum. So we've learned a lot since 2009, 2010 when I was writing the book, and many exoplanet researchers are very much looking forward to James Webb Space Telescope, to Plato and to Ariel, while using data from TESS and CHAOPS. The next thrilling installment of this update is going to be given by a very excellent new appointment that we made last year. So Dr. Joe Barstow is going to give an update lecture on transmission spectroscopy, in particular with the James Webb Space Telescope, which we hope will launch soon, and with Ariel, which is the mission that is at the very right-hand side of this graphic. And both Joe and I are intimately involved in the work towards developing Ariel. So the next thrilling installment, I think, is in about a week's time. I don't know exactly when it's been scheduled, but I think it's coming very soon. And with that, I will close, and let's have some questions, comments, and discussions.